Solutions. The last thing we talked about last week was concentration. We calculated different concentrations. When we're working with things in the lab, we tend to mix things, or we'll take one solution and add extra water to it. When you do that, things get diluted. Okay? If I have a solution, let's say it's a 5 molar solution, and I add water to it, what direction is the concentration going to go? Is it going to be more than 5 or less than 5 molar afterwards? Less. I'm adding water. If I add water, the volume goes up, but the moles don't change. And so molarity is moles over volume. If the bottom goes up and the top stays the same, molarity goes down. Okay. Also, just visually, you can hopefully see that. If I have a concentration and I add water, it's going to get less concentrated. Okay? And then not even thinking in chemistry terms, in real life ideas, you add water to something, it becomes less concentrated. It gets diluted. Dilution is a term that you are familiar with, probably. So the equation for dilution is another one that is not on the cheat sheet. But luckily it is very easy. M1 V1 equals M2 V2. If you look up the dilution equation online or in your book or somewhere else, it's possible that instead of M's, they will have C's. The C that they put stands for concentration. Okay? You can use the same exact equation no matter what unit you're using for concentration. For us, it's always going to be molarity. And so I put the capital M into molarity. So this is molarity 1 times volume 1 equals molarity 2 times volume 2. And the 1's and the 2's, just like our gas laws, are before and after. So this is molarity before dilution times your starting volume, how much solution you started with, equals molarity after dilution times the new volume. And so as you dilute, the volume, the final volume is going to go up, and so molarity will go down. They go in opposite directions. When you dilute, volume goes up, molarity goes down. So just like in the gas laws, we have four variables. You'll be given 3 of them, solve for the 4th. Dilution problems are not difficult. The reason this equation is what it is if I have a solution, and I said 5 molar, there is a certain amount of moles of my solute in there. And if I don't change the number of moles in there, all I do is add water. The number of moles of my solute will not change. And so because molarity equals moles over volume, moles equals M times V. And we said that doesn't change, because that's what's dissolved in the water. If I have salt water and I add extra water, the amount of salt in terms of moles doesn't change. If there's 3 moles in that glass and I add water, there's still 3 moles of salt in there. And so M times V always has to stay constant. That's where this equation comes from. Like I said, it's just a matter of solving for a variable. You'll be given 3, plug them in, and you'll get the 4th. I've rearranged them already, but my guess is you're better off memorizing the 1 and then rearranging it as you need to. So here's an example. We are starting with 175 milliliters of a 1.6 molar solution of lithium chloride. And it says we dilute it to 1 liter. Determine the new concentration of the solution. So if our equation is M1 V1 equals M2 V2, which variable are we trying to solve for? M2. We know what our final volume is. The question is, what is the concentration once we dilute it? So we have to be given the other three. Like with the gas laws again, for the volumes, it doesn't matter whether we use liters or milliliters, as long as we use the same on both sides. So in this problem, we're starting with 175 milliliters, but we're ending with 1 liter. So we're going to have to convert one of those to the other one. Which one do you want to convert? You want to go milliliters to liters? Okay. So if M2 is what we're looking for, we need M1. What is M1? 1.6 molar. What is V1?
1.
It's 175 milliliters, which you said you wanted to convert to liters.
0.175.
0.175 liters. Divide by 1,000. And then we also need V2. 1.0 liters. So we've got our three numbers. We can plug them in. We get 1.6 times 0.175 equals M2 times 1. What does M2 equal? Point 3?
0.28.
Point
0.28, but it's 1/6 as well.
No, we got 2 6 there. That 0 is
Oh, yeah,
1.28. 1.28 is what?
And
Big or little m? Big. Molarity. And that's a dilution problem. You can obviously change the wording around a little bit so that you're solving for any of those. But in reality, it's just figuring out which one you're looking for, write down your other three, plug them in, solve them.
That's not going to go much harder than that.
No. There's another example. It says we need to make 10 liters of 1.2 molar KNO3. And then the wording says, if we're starting with a solution and we want to use 2.5 liters of our starting solution, how much of it do we need to use? Okay? So we got the same dilution equation there. Which variable are we solving for this time?
And yeah, that's it.
Yeah, you got your liters and your liters, and you don't know whole molarity. So you're obviously missing the molarity.
We're missing the molarity. But which one is it? It's M1. Mathematically, it's not going to make a difference if you get 1 and 2 backwards, as long as you pair the right molarity with the right volume. Okay? If you say you're looking for M2, as long as you put this as V2, you're going to get the right thing. But based on what is written here, what it's saying is we need to make 10 liters of that. This is our ending. So technically these are our 2s. That's M2 and V2.
Oh, but it wouldn't matter, so it's.
But mathematically it doesn't matter.
Okay.
And so we are trying to solve for M1. So we have to have everything else. So what is V1?
Oh, but
No,
yeah.
2.5.
2.5. M2, 1.2 molar, and V2, 10.0 liters. We can just plug them in. We get M1 times 2.5 equals 1.2 times 10.0. M1 equals what? 4.8 molar. can do these dilution problems. This one says we're doing an experiment, and we need 100 milliliters of 3 molar hydrochloric acid. What I have on the bench is 10 molar of hydrochloric acid, and I can tell that there's 13 milliliters of it. The question is, can I do my experiment? How would you figure that out? There are a number of ways you can go about this, and they're all going to lead to the same answer. I mean, we have M1, M2, M1, V1, M2, V2. So we're not really missing anything. So what am I doing?
You're diluting.
I'm diluting. But in terms of the problem itself,
It's like a ratio, right?
Oh, it's a ratio.
you can do it in a ratio. I'm not sure if ratio is the best way to do it this way.
Percent? That's what it looks like to me. Right. I think you have enough.
What I would do, you're given 4, right? If you ignore one of them,
Oh, wait, you can like, it's a.
you can calculate what that number needs to be, and they compare it to what it actually is.
So it's kind of like trial and error, like.
Yeah. And so the way I would do it, I see 2 straightforward ways of doing this. I can say, if I take these, if I take what I start with and I dilute it to 3 molar, how much do I get? Do I get more or less than 100 milliliters? If I get more than 100, I have enough. If I don't get 100, I don't have enough. Another way to do it is, if I say I need this much, how much of my 10 molar do I need? If I need more than 13, I don't have enough. If I need less than 13, I have enough. Of those 2, which one makes more sense in your mind? First one? Okay. So, in that case, we said, we're going to figure out how much of this we can make and compare it to how much we need. So in that case, which of these variables are we going to ignore and solve for? Which 2? V2. So what is M1? M1 is 10. V1 is 13 milliliters. M2 is 3. And so we get 10 times 13 equals 3 times V2. So V2 equals what? 130 divided by 3. Not 100. 43.
23.
And we only got 1 sig pig, so 40. No. So what does it, how do you interpret that number? What does that number mean?
You only have 43 milliliters, that's all you're going to get out of it.
Right, that means that we can only make 43 milliliters of 3 molar hydrochloric acid. Now, imagine this is an exam. What would you put as your answer?
You cannot do it.
You cannot make it. Make sure that you answer the question given. Yes, you had to do the math to get it. But the question that you're actually being asked is, can you do the experiment? And so if you do this and stop there, you didn't actually answer the question. So make sure you read what it is asking.
So the reason you couldn't do the experiment is what, because our V2?
That means we can only make 40 milliliters. Because it has to be 3 molar to end with. We can only make 40 milliliters of 3 molar solution. That's all that we have to make. That's all we can do. When we talk about dilutions in lab, we talk about them in terms of dilution factors. Okay? There are a number of ways that we say it in words or if we write it down, okay? One way we do it is we say it's a something full dilution. What I mean by that is if you double the volume of something, if I double the volume of a solution, what happens to its molarity? It gets cut in half. If you increase the volume by a factor of 2, the concentration is going to go down, right? We said when you dilute something, concentration goes down. If you increase the volume by a factor of 2, the concentration is going to go down by a factor of 2. So if we double the volume, we call that a two-fold dilution. If we triple the volume, we call it a three-fold dilution. If we take the volume and multiply it by 10, it's a tenfold dilution. Okay? We can just substitute the word fold for x. A 2x dilution, 3x dilution, 10x dilution. If I tell you you need to do a 20x dilution, you just take whatever your starting volume is, and your V2 would be 20 times as much. What that number is just the ratio between the old concentration to the new, or the ratio of the new volume to the old volume. Okay? It's going to be the same number. It's just remember that volume goes up and concentration goes down. So if I take 10 milliliters of a solution and I dilute it to 100 milliliters, what kind of dilution did I do? It's a tenfold dilution. Does everybody see that? 100 is 10 times larger than 10 milliliters, and so it's a 10x dilution, or a tenfold dilution. Looking at this picture, if I tell you there's a dilution going on here, is the dilution going this way or that way? Just like you're reading, 1, 2, 3, 4, right? If something is colored, you can picture that dilution. That's something that you know is going to happen. If we have a clear solution, the same thing is happening. You just have to remember, because you can't see it, we talk about it in concentration, not in how strong the color is. Okay. So that's dilutions. We then move on to what we call colligative properties. A colligative property is a property of a solution that doesn't matter what it is that's dissolved in it. All it depends on is its concentration. And when we talk about concentration for colligative properties, we're not even going to talk about just molarity. We're going to talk about concentration of the particles in that solution. This is something we've already done, but it's one of those ideas that, even though it's very simple, once you get it, if you don't get it, if it doesn't click, if it hasn't clicked yet, it's something that can trip you up. If I dissolve sodium chloride in water, what do I get?
Aqueous solution or aqueous.
It's aqueous.
The dissociated
It
ion.
dissociates. What does it dissociate into? I get a sodium ion and a chloride ion. When we talk about particles, that's one particle, that's another particle. Okay? So you need to figure out, once you dissolve it and it breaks up into its pieces, how many pieces do you have? Okay? That's what we mean by particles. And there are 4 of these colligative properties. We'll talk about each of them. You have osmotic pressure, vapor pressure lowering, boiling point elevation, and freezing point depression. We're going to start with, hold on, missed the slide. And so this is what we're talking about, colligative properties with strong electrolytes. What's a strong electrolyte?
If they like completely dissociate.
Completely dissociates. So that's going to be an ionic compound. Okay. For these types of problems, I'm either going to give you an ionic compound that completely dissociates, or I'm going to give you something that's obviously a molecular compound that does not dissociate at all. I'm not going to give you something that partially dissociates, okay? That's second semester chemistry, not first semester chemistry. So a strong electrolyte completely dissociates. So the number of particles is really just the concentration of our solution multiplied by the number of particles you get out of it. And we'll see some examples of them. So imagine we have 1 molal, the little m, solution of magnesium chloride. If I dissolve magnesium chloride in water, how many particles do I get out of it? I get 3. What are they? I get 1 magnesium in 2 chlorines. These 2 chlorines end up as 2 separate chloride ions. So I get 3 particles. So if you wanted to tell me the concentration of particles in that solution, it's really easy math, what would you do? 3. I start as 1 molal. I go 1 molal times 3, because I get 3 particles, is 3 molal. That's all it is. Take the starting concentration of your solution, multiply it by how many particles you get out of it. If instead of 1 molal magnesium chloride, if I had 1 molal sucrose, how many particles does sucrose break into? That's a molecular compound. It doesn't. Molecular compounds don't break up. And so it just becomes 1 molal times 1 equals 1.
Is that what you take the number of?
Now, take the concentration of your solution,
Yeah.
multiply it by the number of particles it breaks into. First, we'll get a property as osmotic pressure. This is, in my mind, the hardest one to wrap your head around. Okay? So this deals with osmosis. In osmosis, solvent molecules, we're going to be dealing with water solutions. So aqueous solutions, so our solvent is the water. Okay? In osmosis, our water is going to move. And we say it moves through a semi-permeable membrane. We call it semi-permeable because it lets some things through while other things don't go through. In this case, the water can pass both ways across the membrane, but whatever is dissolved in the water, whether it's sugar or sodium chloride or whatever, it can't move. So whatever was dissolved in the water is stuck, but the water can move back and forth. If you put 2 solutions on either side of a semi-permeable membrane. So in this picture, we have this funnel upside down with our membrane. We put it in a beaker of distilled water. And so if the membrane is here, we have 2 solutions on either side of that membrane. We have a 3% salt solution on the inside and distilled water on the outside. In osmosis, the water goes towards the higher concentration. Okay? Water will always move times towards the higher concentration. It will move towards the salt, or it will move towards the sugar. And so what we see here is, in this case, the salt, the higher concentration inside the funnel. And so the water from the beaker crosses the membrane into the funnel. And so the water level in the beaker goes down, and the water level in the funnel goes up. Where osmotic pressure comes from is we have the water over here. It's just pure water. It wants to get over to this side. It wants to get over here with a solute. But that membrane just has holes in it. Okay? The water can't go through just anywhere. it has to go through a hole. And so you have the solvent molecules, the water over here, they're going to bump into that membrane, just like the gas does bumping into the inside of the balloon. When those water molecules hit that membrane, they push on it. When they push on it, they create pressure. And the more this water wants to get over there, the stronger it's going to push. And so the more the water wants to get over here, the higher the osmotic pressure. Think of it as people on Black Friday trying to get into Walmart, okay? There's one door, and everybody wants to get through the same door, and so for some reason, the crowd just pushes on the glass around. You get enough pressure, if the TV is cheap enough inside, they're just going to break the window and go in, okay? The more the water wants to get through, the higher the pressure, okay? That's the way I think about it. The way other people can describe it is, to me, it's almost like a double negative. It's the pressure that you have to push on this side to keep the water out. So it's like if you're the security guard at the Walmart and you have to keep this customer out, how hard do you have to push on that door to keep them from pushing it in? Okay. But in terms of physics, just forces, that number is the same. Okay? If you're pushing in and I'm pushing out, and the door is not going anywhere, we're both pushing with the same force. So for osmotic pressure, it doesn't matter which direction you're looking from. Okay? They're both equally valid, and it's the same number. In general, the larger the difference between these concentrations, the larger the pressure. And so if you have two salt solutions whose concentrations are very, very different, very, very slightly different, they're almost exactly the same, it's going to be low pressure. So if you put a salt solution with distilled water, there's a big difference in concentration, so you have a lot of osmotic pressure. Okay? If we take this system and we look at it a little bit different, instead of a funnel and a beaker, we just take kind of an elbow-shaped tube or a U-shaped tube. We put the membrane right in the center. And we put two solutions on each side. We have a solution over here and pure water over here. Which direction does the water want to go? Left to right or right to left?
Left to right.
Left to right. It wants to go to the solution. So the water over here will go over there. And so this drops, and that goes up. What they're trying to show here is if you were to calculate that osmotic pressure that's being put on that membrane, and you push with the same force over here, you would go back to equal. Okay? My suggestion in terms of thinking of osmotic pressure is to think about the water molecules pushing on that membrane, trying to get through. In my mind, that's a simpler explanation, but it's equally correct. You will not have to calculate osmotic pressure on a quiz or an exam or a final, okay? But this is the equation, okay? That's a pi. Pi is the symbol for osmotic pressure. I is the number of particles you get. So for sodium chloride, it's 2. For sucrose, it's 1. For magnesium chloride, it's 3. Plug that in for I. R is the gas constant, the same exact one we already used, 0.0821. T is temperature, and M is molarity. Some people like to take the I and the M, combine it together, and make osmolarity. Don't worry about it. And so, an osmole is a particle, okay? When we took 1 times 3 equals 3, what we were actually calculating is the osmolarity. Okay? But you don't need to worry about that. We're going to skip this slide.
So osmolarity is just like something for our own knowledge if we want to know about it, but we don't like have to know about it.
You have to know it according to the learning objectives. Where this really comes in especially in the medical field, is when you're putting things into people through IVs, okay? Your blood has a certain osmotic pressure. And if you infuse someone with something that has a very different osmotic pressure, you're going to cause problems. So what we call an isotonic solution means you have a membrane, and the concentration inside and outside is the same. That is your goal when you're putting something like saline into a patient. Okay? A hypotonic solution means that the inside is more concentrated. Hypo means low or too low. If it's a hypotonic solution, the concentration of your solution on the outside is too low. And the opposite is hypertonic. In a hypertonic solution, the concentration outside is too high. So if we think about this in terms of a red blood cell, a red blood cell normally looks like that. It looks like a donut with a kind of a thumbprint in the center. If you put a red blood cell into an isotonic solution, there's no osmotic pressure, water doesn't flow either way, and it stays looking like that. If you put a red blood cell into a hypotonic solution, that means the inside is more concentrated. Water moves towards the concentration. And so the water is going to move into the blood cell. When the water moves into the blood cell, it will expand. If it expands enough, it'll blow up. Yes, it does happen. No, you don't want it to happen. If you put it into a hypertonic solution, so if you make up a solution that's too concentrated, inject it into your patient, the water is going to come out of the red blood cells into the bloodstream, and your cells are going to shrivel up. That's not quite as bad because cells can, once they shrivel, they can re-expand. Once they blow up, they can't unblow up. But if the patient's dead, it doesn't matter. So you need to make sure your solution is isotonic. Okay. That's osmotic pressure. Then we have vapor pressure lowered. We said vapor pressure was how much of our liquid evaporates and forms gas up here. If we take that water and we dissolve something into it, here we have pure water, we dissolve something yellow into it. What that does is it prevents some of this water from evaporating. And so it reaches equilibrium sooner. It reduces the vapor pressure of that solution. So if you're ever at a party and you're bored and you want to bet somebody that you can move water from one glass to another without touching either of them, you can do it. You just better hope it's a really long party because it's going to take a long time. If you take a glass of water and a glass of sugar water, put a lid over both of them, because this has a higher vapor pressure, this is going to evaporate up here, end up back in there, and eventually the water over here will end up over there. It's going to take a long time.
Will that work with salt?
Yeah, anything you dissolve in it will work. The hotter it is, the quicker it'll go.
Like how long? Like days or hours?
Days.
Lots of days.
You want to win the bet, though.
Some party.
Third one is boiling point elevation. So think when you dissolve something in your water, the vapor pressure goes down. It prevents that water from evaporating. So boiling point elevation is very, very similar to vapor pressure lowering. If that water no longer wants to evaporate, but you want it to evaporate, so you're going to make it boil, you're going to have to heat it to a higher temperature to make it evaporate. That's what this says. It says when you add a solute, the boiling point will change because you change the vapor pressure. And so when you dissolve something in your water, the vapor pressure will go, the boiling point will go up. You can increase the boiling point of a liquid by dissolving something in it. Can you think of an example of when you do this in real life? You add salt to your water when you boil spaghetti. Did you know why you were doing that? Most people think it's for taste. But think about it. How much water is in your pot of spaghetti? A lot. How much salt are you adding? Not much. You're not going to taste that salt. Okay? When you add that salt, you raise the boiling point of your water. And so your water is boiling at a higher temperature. If your water is boiling at a higher temperature, your pasta will cook faster.
Is that with anything that you put in the water?
If it dissolves, yes. Whether it could be sugar, it could be turpentine, whatever you want to add. I don't suggest adding turpentine to your spaghetti, but if it dissolves, because we said colligative property does not matter what it is that's dissolved.
Okay, so like when you add oil to the water so that the pasta doesn't stick together.
The oil won't dissolve though.
No, because you just.
It has to be something that dissolves.
So it increases the pressure?
It increases the boiling. The water, your spaghetti tap water, would normally boil at 212 degrees Fahrenheit. If you add some salt, maybe now it's boiling at 220, 230.
So increasing the boiling point of a liquid, making the vapor pressure increase?
No. If you add salt to your water, the vapor pressure lower. But think about the names.
So it's lower.
The names will tell you which way things go. It's vapor pressure lowering. So when you add the salt, vapor pressure goes down. It's boiling point elevation. And so when you add salt, the boiling point goes up. The last one is freezing point depression. So when you add salt to water, which way do you think the freezing point is going to go? Down. Can you think of an example where people use this to their advantage?
Salt on the road.
Salt on the roads.
Oh, I'm sorry.
If you live up north, they
If-
put
if-
salt on the
If
road.
you live up north,
Yeah.
if you live up north, when it starts to get cold and the roads are wet from melting snow or rain, they'll put salt on the road. That salt dissolves in the water, lowering the freezing point. So instead of freezing at 32 degrees, maybe now it'll freeze at 25 degrees. And so you get an extra 7 degrees where the roads aren't frozen. But it doesn't permanently make that water, prevent that water from freezing. If it gets cold enough, it will still freeze. What happens if it gets really cold? What do they put on the road?
Like brine, right? Or no, that is the salt.
Well, actually, they'll put sand.
Yeah.
So that way the sand just gives you better traction on the ice.
So,
Good luck.
The salt doesn't last, so if they drop salt at 2 in the morning.
No, they have to continuously do it.
Right.
They do like a pre-treat with brine, and then they like add stuff. I lived in Indiana, and it was horrible.
I grew up in Michigan. I never saw them put brine.
Well, at least where we live, they put like the salt solution on, like before it started snowing and stuff, as early as they could.
That's what they do in North Carolina.
There's one more example here. Anybody else have one more way this has been used? Mythbusters did it.
I would just put it in a cooler of beer.
Cooler of beer. Why would you do that?
Makes it colder.
Makes it colder.
Why?
Putting salt in
Freezing point, so instead of it being 32 degrees.
Well, I would do
Yes.
Colder.
With just pure water, ice is 32 degrees. If you put salt in there, it now freezes at a lower temperature.
Who puts
It's-
salt in their food? I don't think I've ever had someone who put.
Now your ice water in your cooler is maybe 25 degrees. And so when you put your drink in there, it's going to get colder faster, or it's going to get eventually it's going to get even colder than 32 degrees.
So with ice cream, you make ice cream at home?
When you make ice cream at home, you put salt with your ice so that you can get your ice cream colder than the ice was when it came out of your freezer.
I don't know how to do that.
So it lowers the temperature.
Yes. Last slide.
Last one.
Thinking about what colligative properties mean, okay? which of these solutions is going to have the higher boiling point? Why B?
Has the biggest amount of salt
Has the most part, well,
concentration.
starting concentrations are different. So what you have to do is you have to take the concentration, multiply by the number of particles. So you've got 0.2 times 4 is 0.8. 0.5 times 5 is 1. No, 2.5.
Yeah.
5 times 5? 5 times
4 times
Oh,
point,
2.5.
2.5. And then we've got 0.3 times 3.
That one, the first one would be 0.2 times 4.
0.2 times 4, 0.5 times 5, and 0.3 times 3. This one's 0.6. So that one is the most concentrated. And so it will have the highest boiling point. So boiling point elevation. The higher the concentration, the higher the boiling point. Which one will have the lowest freezing point? B. It's boiling point, it's freezing point depression. So the one that's the most concentrated will change the most. Go on.
Which one's the highest again? B?
B is both.